Okay, good morning, Chem 30. We are now looking on section 5.2 out of your textbook, or qualitative change in equilibrium systems. Okay, really, it's all based on Le Chatelier's principle, which we'll talk about here in a minute. Okay, so again, a system at equilibrium must be closed. Okay, so like it can't be giving off, there can't be any materials being transferred in and out. So at equilibrium, the amount of reactants and products remain the same. The volume and pressure of the system is constant, and the temperature does not change. Okay, so really, like the forward and reverse reaction is at the same amount. It's going forward at the same amount as it's going reverse. Okay, and then yeah, like you can't change the temperature or can't change the volume or anything like that at equilibrium. Okay, because if we change any of these factors, it changes our equilibrium. That's what we're going to be talking about today. Okay, basically, you can think of it like if you've ever walked up an escalator before, okay, or if you ever walked up the down escalator before, okay, you can get to a point where if you're walking at the same speed of the escalator, you just are staying in the same spot. Kind of like if you're walking on a treadmill, like you're walking in the middle. If you walk too fast, excuse me, you would walk off the front. If you walk too slow, you would fall off the back. Okay, so at equilibrium is when you're walking at the same speed right in the middle. Okay, if you change any factors, if you start going faster, things change. If the treadmill goes faster, the escalator or whatever you want goes faster, okay, you have to change. Things have to change to then be back at equilibrium. Okay, so the French chemist Henry Le Chatelier, he experimented with various chemical equilibrium. Okay, in 1888, okay, he summarized his work on changes to equilibrium in a general statement that we now call Le Chatelier's principle. Basically, it is a dynamic equilibrium tends to respond so as to relieve the effect of any change to the condition that affected the equilibrium. So Le Chatelier's principle qualitatively predicts the way that equilibrium system will respond to change. Okay, and so we're going to use the example of the Haber-Bosch process to kind of look at what that change is, or like how that change affects equilibrium. And so the Haber-Bosch process basically is for making ammonia. And so we have nitrogen and hydrogen, okay, go together to make ammonia, okay, which is then used in different types of fertilizers and things like that. So at 500 degrees Celsius, it says our equilibrium constant is zero point 0.4 degree or zero point 0.4. There's no units for it, so it's just 0.4, meaning that like it's really close to one, okay, and so it really, I'd say it favors the reactants a little bit, but like it's really kind of in the middle there. Okay, so ammonia can be removed from the mixture of gas by cooling, since ammonia liquefies before nitrogen does. So if we want to get rid of some of this ammonia and we change the temperature, basically what's going to happen is the amount of ammonia would remove, or like, yeah, we're going to reduce the amount of ammonia in here. Okay, if we reduce the amount of ammonia, okay, then these two, there's still more of these reactants, they're going to basically shift and produce more ammonia. Okay, the ammonia is then used to make fertilizer. Okay, and then yeah, today more than 1/3 of all people on Earth depend upon fertilizer produced by the Haber-Bosch process for their food. So to make this commercially viable, the Chatellier's principle is employed. So basically, there's different things that we can change to produce more ammonia. We want more. Okay, and so the first one, as we kind of talked about, is remove the product. So remove ammonia. Initially, the system will no longer be at equilibrium. Le Chatelier's principle predicts a shift in the reaction to relieve the change because the dynamic equilibrium is always taking place at the molecular level. Equilibrium will then continue until it's reestablished. So, to return to equilibrium, the concentration of ammonia must increase. Okay, since we're taking some of the ammonia out, we have to then replace it with new ammonia. Okay, this system will respond to the removal of ammonia by forming more ammonia or shifting to the right, which we just call the equilibrium shift. Okay, the value of the equilibrium constant stays the same. Nothing happens, so it'll be unchanged as long as the temperature of the system is returned back to like our 500 degrees. So they cool it down to take out some of this ammonia, okay, but then they heat it back up so that we get the same Kc and the shift is accounted for then. Okay, another change, if we want to make more ammonia, is to add a reactant. So initially, the system is no longer at equilibrium. Le Chatelier's principle predicts a shift to relieve the change because the dynamic equilibrium always wants to change to reestablish equilibrium. The system can do this by shifting to the right and forming more ammonia, which makes sense. We add more reactant, we're going to produce more product. Again, the value of the equilibrium constant doesn't change. Kc doesn't change. All we're doing is adding more reactant, which will produce more product. So the ratio stays the same. Okay. Another thing that we can do is to decrease the volume. Okay, or another change that happens. So if we decrease the overall volume, which is to increase the pressure, we can then change our equilibrium. So when the volume of a mixture of gases decreases, the pressure of the gases must increase, okay, according to Boyle's law, which we talked about in Unit 2. So initially, the system is no longer at equilibrium. Or sorry, that was Unit 2 last year that we talked about that. But yeah, so anyway, the system's no longer at equilibrium. Le Chatelier's principle predicts a shift in the reaction to relieve the change. So the shift must reduce the pressure of the gases. So the molecule striking the walls of the container is what causes that gas pressure. So if we reduce the number of molecules at a constant temperature, it's going to go to whichever side has less molecules. So given the equation, again, for the Haber-Bosch process, where we have nitrogen and hydrogen produce ammonia, there are 4 moles of gas on the left-hand side. So again, there's a 1 here, plus 3, we got 4 moles. Over here, there's only 2 moles because of the coefficient. Okay, so there's 2 moles of gas on the right side. So if we increase or decrease the volume, which increases the pressure, okay, the equilibrium is going to shift to the right because the pressure of the mixture decreases with the more ammonia that's made because there's less ammonia on that side. So again, it's always just going to shift to whichever side has less moles. And this is only like if we're changing the pressure, which the only way we can change that pressure is by changing the volume. Okay, so reducing the volume, equilibrium mixture of gases at constant temperature causes a shift to the reaction in the direction of the fewer molecules of gas. Okay, if it ends up that you have the same amount, then really there won't be any shift. Okay, again, the value of the equilibrium constant doesn't change. Okay, it still has the same ratio, but like in this case, if we change it, it's going to produce more product, okay, and some of the reactants will go down. All right, and the last change we can do is to decrease the temperature. So the value, or I guess change the temperature in some way. So the change in equilibrium constant changes with temperature because the rates of the forward and reverse reaction are affected. So changing temperature is the only thing that will actually change the equilibrium constant. Okay, so Le Chatelier's principle can be used to predict the effect of temperature change on a system when the enthalpy change for reaction is known. So for the Haber-Bosch process, it's exothermic, which means that our energy is on our product side. So if we decrease the temperature, basically we're taking some of this energy away. Okay, so the energy would be going down. You can think of energy as like a product. Okay, and so if we reduce, like if we were to take some of the ammonia away, it shifts back, or it shifts to the right. If we take some of the energy away, it's also going to shift to the right. So the decrease in the temperature results in less energy, so the reaction will shift to the right. Since it shifts to the right, okay, our equilibrium constant increases. Okay, a change in temperature is the only change that causes a change in equilibrium constant. Okay, you need to remember that. That's going to be on a quiz or a test. Okay, and just be careful with that. So by decreasing the temperature to increase the production of ammonia, the reaction rate also slows and the process becomes uneconomical. So Haber overcame this by adding a catalyst. So we talked about what catalysts do in our first unit. Okay, catalysts reduce the amount of energy that's needed for this process to happen. Okay, so the addition of a catalyst speeds up the rate of reaction by either allowing a different reaction mechanism or providing additional mechanisms. So the overall effect, okay, is to lower the activation energy, which increases the rate of reaction. However, the activation energy is lowered the same amount for the forward and reverse reaction. So again, the K seed is ineffective. The same increase in reaction rate occurs both ways, and so the addition of a catalyst has no effect on the position of the equilibrium. The only effect is to decrease the time it takes to achieve this equilibrium again. Okay, so kind of a summary of our Le Chatelier's principle and the variables that affect chemical equilibrium. Okay, so if we change the concentration, if we increase the concentration, it will shift to consume some of the added reactant or product. So if we, like in the example we did, if we increase the amount of reactant, it's going to produce more product. If we decrease the concentration, it's going to shift to replace some that was removed. So again, at the Haber-Bosch process, if we take out some of our ammonia, it's going to shift and produce more ammonia. Temperature, if we increase it, it shifts to absorb the added energy. Okay, so for this, the biggest thing for temperature is knowing whether it's exo or endothermic. Okay, if you increase the temperature, you're increasing the energy, so it's going to shift to relieve some of that extra energy. So like in our case with our Haber-Bosch process, if we increase the temperature, we would actually shift it towards the reactants, which we wouldn't want to do. Okay, if we decrease the temperature, it's going to shift to replace some of the removed energy, and so it would shift towards the products. Okay, and again, temperature will change the amount or the Kc value. And then the last thing we can change is volume. Okay, this only works for gaseous systems because then gas and pressure are kind of indirect or related, directly proportional. Okay, so if we increase the volume, which is to decrease the pressure, it shifts to the side with larger total chemical amount of gaseous entities. If we decrease the volume, which is to increase the pressure, it'll shift to the side with smaller total chemical amount of gaseous entities. All right, so that's Le Chatelier's principle, along with the summary. I'm going to do more examples on the next video, okay, of just kind of how I would answer these questions.